Here are various topics within Chapter 4. In this video, I'm going to discuss concentration of solutions. Within the overview for the chapter, concentration of solutions is an important idea that supports our analysis of titrations. When I look at the learning objectives for this chapter, I find that students' ability to calculate the concentration of solutions is quite high. Students are able to calculate the concentration of a solution, but you notice titrations, that's the most difficult idea within the entire chapter. As an instructor, I'm going to try to help bridge these two. Let's see if we can develop a strong understanding of concentration of solutions, not in isolation, but then how it can also support other kinds of questions, such as our ability to answer questions involving titrations. So we've already explored a little bit with this PhET sim, what happens when various electrolytes dissolve in water. We saw that within the sim we had a faucet at the top, faucet at the bottom. We could measure the water level. We could promote evaporation, add a solute, and record information, record data about concentration. So within this particular video, we're going to be very interested in that concentration portion. Let's look at an example. The solute is calcium chloride. There's a particle level description for how it dissociates, and we have concentration data. Initial questions for you. Why is chloride aqueous in the solution? Shouldn't calcium chloride produce Cl2? The formula is CaCO2. Why do I get chloride ions, not Cl2 molecules? Second, why is the concentration of chloride greater than the concentration of calcium ions in solution? Pause the video, share your ideas. Now within the simulation, there's various actions that we can do. We could add water from the top faucet, open the bottom faucet, or allow evaporation. What could happen to the concentration of the solute? Well, I think we have three options. It could increase, there could be no change, or it could decrease. Make a prediction for each of these actions. For a particular action, what is going to happen to the concentration of the solute? Will it increase? Will there be no change, or will it decrease? Stop the video, share your answers. Now let's see what it shows within the sim. We have an action and a potential change to the concentration. So were your predictions correct? And second, which action or actions change both the amount of solute and solvent within this simulation? Explain what's going on. Which action or actions change both the amount of solute and solvent? Pause the video, share your answers. So why have I returned to the sim? Within the overview of the chapter, the sim was used to support our initial understanding for strong, weak, and non-electrolytes and connect this chemistry triplet of observations that were macroscopic, particle level, and formulas and equations. I came back to the sim for a few different reasons. I wanted to make clear that concentration describes the amount of solvent relative to the amount of solvent, or it could be relative to the total volume of the solution. We're interested in a ratio like that when we're analyzing concentration. Second, we need to think about the particle level description, not just the numbers. Many times I see students get on the wrong path here. As soon as numbers are presented in a concentration scenario, they fixate on the numbers. We always need to think back to what's taking place at the particle level. And a very common error I find is failing to account for the manner in which the electrolyte dissociates. So I specifically chose calcium chloride to pay attention to how it produces chloride ions, and we had twice as many chloride anions as we had calcium cations. Here's some calculations on this subject. Which will have the highest concentration of potassium ion? So I notice within here I have different formulas and different concentration values given. I have different sets of numbers and different formulas. Let's see if we can build an understanding to be able to answer a question like this. In section 4.5, when we're looking at concentration of solutions, we're going to be using units. We will be using units called molarity. The definition for molarity, which is given the symbol capital M, is moles of the solute for every 1 liter of solution. Here's an example question. 17.61 grams of sodium chloride solid is dissolved in a 500 ml volumetric flask, which is filled to the line with water. And we have information, molar mass given for sodium chloride. A volumetric flask is one where when we fill it up to the line, we know the total volume of the solution. So they have specific volumes, a single specific volume, and in this case, a 500 ml volumetric flask was used. How many moles of chloride are going to be in the flask, and what is the concentration of the sodium chloride solution? I always want to begin by thinking what's taking place at the particle level. I'm taking the solid salt. When it dissolves, it will become aqueous, and I will say that when it dissociates, it will dissociate into sodium ions and chloride ions in a 1-to-1 ratio. How many moles of chloride are in the flask? Low dimensional analysis to tell me how many moles of sodium chloride I have. It dissociates 1-to-1, so this would be how many moles of chloride are in the flask. What would be the concentration of the solution? I have a certain number of moles of sodium chloride in half a liter, so this would be the molarity of the sodium chloride solution. I'm putting that there in red to designate I need to think back what's taking place at the particle level. I can talk about the concentration of 0.6026 molar sodium chloride, but at the particle level, they've dissociated. So even though I'm writing that together as aqueous, as soon as I see the aqueous symbol, I'm thinking of separate sodium ions, chloride ions, but I can still discuss then the concentration of the entire solution. Here's a typical question on this topic. Pause the video, give this one a try. What is the molar concentration of the sodium ions in that solution? I would begin by asking, how does it dissociate? It's a strong electrolyte, and this would be a description for how it dissociates. If I start out with 2 moles of the sodium sulfate, it'll give me 4 moles of sodium ions and 2 moles of the sulfate. This is asking about the concentration for the sodium ions. Here would be my calculation for the molarity. Key step in this, where students would make the mistake, is jumping past accounting for the manner in which the strong electrolyte dissociates. Next idea. We saw previously when we looked at balanced chemical equations that moles react with moles. So consider this question. We have hydrochloric acid reacting with sodium hydroxide in a neutralization reaction. How many grams of sodium hydroxide solid are needed to completely neutralize half a mole of hydrochloric acid? And the molar mass is given for the sodium hydroxide. When I look at that balanced equation, 1 mole of HCl reacts with 1 mole of sodium hydroxide. So I can quickly see that I'm going to need half a mole of sodium hydroxide, and given the molar mass, that would be 20 grams. the key part of this question is the molar mass. If I have grams and I want to get it into moles, grams of a solid, I will look to the periodic table, or it was easier in this case because the value was given, I'm going to use the molecular weight or the molar mass. What if the question's changed and instead of having solid sodium hydroxide, it's aqueous? How many mils of 0.25 molar sodium hydroxide are needed to completely neutralize that same half a mole of hydrochloric acid? In this, we're going to use the solution information to get to moles. Anytime we have a balanced equation, moles reacting with moles, we need to either convert from grams into moles or use the solution information. So molarity is defined as moles per liter, moles of solute per liter of solution. Molarity, that's the description of the concentration. So if we just manipulate that slightly, we can see that the concentration times the volume gets to number of moles. This is a really important relationship for us. In this case, we still need half a mole of the sodium hydroxide because in our balanced equation it's 1:1. The concentration is given as 0.25 moles per liter. That's the molarity of 0.25. We only have one variable left, which is the volume. We can set up a simple ratio and solve for the volume as being the moles of the sodium hydroxide that we need divided by its concentration. We need 2 liters of the sodium hydroxide solution. Within our scenario here, I think that you're very proficient at using the periodic table to go from grams to moles or moles to grams. The new skill that we want to add is this idea of let's use the concentration and volume to get to number of moles. Solution information includes concentration and volume, and our reaction is still in terms of moles. This is the key for solution stoichiometry. It's how concentration fits in. What questions do you have based on the information on this particular slide? This is going to be our link between thinking about concentration to thinking about titrations. Pause the video. What questions do you have based on this slide? Returning to our earlier questions now, see if you can answer both of these. This is giving us information about concentration, molarity, for different compounds. And the second one, which will contain the greatest number of moles. In this case, we have solution information of both volume and concentration for different compounds.